Alright, let's solve the question above. It says a cast iron beam is of I section as shown below. The beam is simply supported on a span 5 meters. It means the length is 5 meters. If the tensile stress is not to exceed 20 Newton per mm square, the tensile stress, we are told to find the safe uniformly load which the beam can carry, and we are also going to find the maximum compressive stress. So you can see the diagram of the I section. You can see we have the top flange, we have the bottom flange, and then we have the web. All right, so and you can see everything well dimensioned. So for us to proceed with this question, we are going to divide this I section into three rectangles. So and do that by drawing a dotted line here and here, here and here. So here is our rectangle 1, here is our rectangle 2, and here is our rectangle 3. All right, so firstly we are going to be calculating the distance of the center of gravity from the bottom face. And how do we do that? We are going to do that by using the formula above. So y bar is equals to a1 y1 plus a2 y2 plus a3 y3. I hope you know why it is 3. I hope you know why we are stopping at 3, because we have 3 rectangles. All right, so plus a1 plus a2 plus a3. So this our y bar is the distance of the center of gravity from the bottom surface. All right, while our a1 is the area of the first rectangle, and our y1 is the distance of the center of gravity of a1 from the bottom surface, and our a2 is the area of the web, and our y2 is the distance of the center of gravity of a2 from the bottom surface. So similarly, and so on and so forth. All right, so let's start with the calculation of our a1 first. So our a1, which is the area of the first rectangle, you know the formula for a rectangle is length times breadth. So we have 160 and then we have 40. So here we are going to have this to be 40 multiplied by 160. So 40 multiplied by 160 is nothing but what? 6,400. So it's going to be 6,400 mm squared. All right, our A2. So our A2, that is the area of the web. As you can see, this is our web. We have from this point to this point to be 200, while the thickness is 20. So we are going to have this to be 20 multiplied by 200. And 20 multiplied by 200 is nothing but what? 4,000. So we are going to have this to be 4,000 mm squared. All right, so our A3. Our A3 will be equals to, that is the area of the top flange. So it's going to be 20 multiplied by 80. 20 multiplied by 80. And 20 multiplied by 80 is nothing but what? 1,600. So 1,600 mm squared. All right, so we are done with the calculation of all the areas. So let's go for y1. So we said our y1 is the distance of the center of gravity of a1 from the what? From the bottom face, right? So it means that our y1 is going to be 40 divided by what? Divided by 2. So I'm going to have this to be 40 divided by 2. And 40 divided by 2 is 20 mm. All right. So now our y2. Our y2 is the distance of the center of gravity of a2 from what? From the bottom surface. So this is our second rectangle, right? So we are going from the bottom surface. So it's going to be from this point to this point is 40, right? We are moving in the y direction. From this point to this point is 40, so it's going to be 40 plus, then from this point to this point is 200, so it's going to be 200 divided by what? By 2. So 200 divided by 2 is 100. 100 plus 40 is 140. So I'm going to have this to be 140 mm. All right. So our y3 now. Our y3 will be equals to, all right, from the bottom surface to 40 plus 200, then plus 20 divided by what? Divided by 3. All right. Sorry, divided by 2 rather. So we're going to have 40 plus 200, then plus what? Plus 20 divided by what? 2. So this is 20 divided by 2 is 10. So this is going to give us what? 250. So this is going to give us 250 mm. 250 mm. So this is how to go about our y1, y2, y3. Please don't mistake. We are dealing with your y1 is the distance of the center of gravity of A1 from what? From the bottom surface. So everything is from the bottom surface. So, and if you look at it, we are just referring to this bottom flange here, which is what? 40 mm, right? So if you divide that by 2, you are going to get your y1. For your y2, you are going to say 40 plus, then the length of our rectangle there is 200. So it's going to be 40 plus 200 divided by 2. And our y3 is the third rectangle. So it's going to be the first rectangle from the bottom surface plus the second rectangle from the bottom surface, then plus 20 divided by what? By 2. So you are going to get 250. I hope you understand this. So let's substitute all these parameters into this formula, because I already told us that our y bar is the distance of the center of gravity from the what? From the bottom surface about the neutral axis. All right. So now our y bar will be equals to our A1. What is our A1? That is 6,400 multiplied by what? Multiplied by our y1. Our y1 is what? That is 20. 20 plus our A2. Our A2 is, let me arrange this very well. I want everything to be clearly written. All right. Now I love my work to be neat. All right. So our A1 is, all right. Sorry. Our A1 is 6,400 multiplied by our y1. Our y1 is 20. Plus our A2. Our A2 is 4,000. Multiplied by our y2. Our y2 is 140. Plus our A3 is 1,600. Multiplied by our y3, which is 250. This, I just want to manage my space. All right. All right. I hope you can see this clearly. All right. So our A1 is 6,400 plus A2, which is 4,000, then plus A3, which is 1,600. All right. So if you press your calculator now, you are going to have 6,400 multiplied by 20. You're going to give us 12800. 12800. All right. So that is what we are going to have. Plus the 4,000 multiplied by 140. We are going to have this to be 560000. All right. And 1,600 multiplied by 250. We are going to have this to be nothing but 40,000. All right. So that is what we are going to have. So divided by, so if you sum 6,400 plus 4,000, that is 10,400. 10,400 plus 1,600. So that is going to give us 12,000, right? All right. So that is going to give us 12,000. All right. So now, if you sum everything here, then you divide by 12,000, you are going to have this to be 90.66 mm. All right. So it shows that our center of gravity, it is 90.666 mm from what? From the bottom face. I hope you understand that. So it means it's going to be around somewhere around this side. So from this point to somewhere around this side. Exactly. So for us to get the top part, it's going to be, you are going to add everything together here, which is 200 plus 40 plus 20, that is 260. 260 minus 90.66, you are going to get the top part. All right. But let's work one after the other. I want us to grab this concept clearly. All right. So we are done with the center of gravity. All right. So the next thing we want to work on is the moment of inertia of the I section about the what? About the neutral axis. All right. So moment of inertia of what? Of the section about the neutral axis. All right. So please, maybe you just write this in full. All right. So this is denoted by I. So because we have three rectangles there, we are going to have this to be I1 plus I2 plus I3. All right. So let's start with I1. So the formula is BD cubed divided by 12 plus A1 into, so here you will always check your distance of center of gravity and y1. You check the one that is greater. So our y bar is greater than our y1. So it shows that here we are going to have y bar minus y1 all squared. So this is the formula for our A1. So let's substitute now. So if you go to our first rectangle here, the base multiplied by our depth. So our depth is 40, while the base is 160. So we are going to have this to be 160 multiplied by 40 to the power of 3 divided by what? By 12 plus A1. Our A1 is nothing but 6,400. Then into our y bar. Our y bar is 90.66 minus our y1. Our y1 is 20. So everything all square. So if you press this carefully in your calculator, you are going to have your I1 to be nothing but what? It's going to be 3280. 7481 point what? 0.17 mm to the power of 4. All right. So that will be our y1. So let's go for our y2. So similar formula. The only thing that will keep changing is here. You always check which one is greater between your y bar and the y2. You check. So the one that is greater will always come first in order to avoid the negative sign there. So we are going to have the formula BD cubed divided by 12 plus A2. We are dealing with the second rectangle now. So let's check between y bar and y2, which one is greater. All right, y2 is greater than y bar. So we are going to have y2 minus y bar all squared. All right. So we are going to have our I2 to be BD for our second rectangle, the depth is 200 while the thickness is 20. So the depth is 200. It means the base is what? Is 20. So we are going to have this to be 20 multiplied by the depth, which is 200 to the power of 3 divided by 12 plus our A2. Our A2 is nothing but what? 4,000. Then into Y2. Our Y2 is 140 minus our Y bar. Our Y bar is 90.66 all squared. Alright. So by the time you press all of this in your calculator, you are going to have your I2 to be nothing but what? 230710 230710 75.73. So our units remain as mm to the power of 4. So our I3 now, our I3 will be equals to, similarly, same formula, BD cubed divided by 12 plus A3 into, so let's check. Our Y3 is greater than our Y bar. So we are going to have Y3 minus Y bar to the power of 2. Alright. So if you make your substitution here, we are going to have the depth is 20 and the base is 80. So here we are going to have 80 multiplied by 20 to the power of 3 divided by 12 plus our A3. Our A3 is 1,600 into Y3. What is our Y3? Our Y3 is 250 minus our Y bar, which is 90.66 all squared. Alright, so if you press this in your calculator, you get your answer for your I1. So alright, so you press your calculator, you are going to have your I3 to be nothing but what? 4067 110 point what? 0.29 mm to the power of 4. Alright, so now we can therefore calculate our moment of inertia about the neutral axis now. So it shows that our moment of inertia will be equals to I1, and our I1 is what? Is equals to 32807 481.17 plus our I2. Our I2 is 23071 075.73, then plus what? Plus I3, which is 4067110.29. So by the time you sum everything together, you are going to have nothing but what? 9655 4667 4667.2 coming, is it 0.21? Okay, 0.21 mm to the power of 4. All right, so this is the value of our moment of inertia about the neutral axis. All right, so now that we have gotten all this stuff, now we can now dive into the question now. So the first question says you find the safe uniformly load which the beam can carry. All right, so before we do that, you are going to recall carefully from our Fleischer equation that says that moment all over I is equals to what? Stress all over what? We're going to make our maximum bending moment the subject here. Our M here is our maximum bending moment. Our I is the moment of inertia. Our stress here, it can be this is our maximum stress, which can be tensile or compressive. This is our Y mass 2. It can be tensile or what? Compressive. Due to this question, if you have your simple your simple supported beam, we know that the top part of our simple supported beam is subjected to what? Compressive stress, while the bottom part is subjected to what? A tensile stress. So if you draw the stress distribution diagram for this I section, the bottom part, from the bottom part to where we have our center of gravity, that is the distance of our center of gravity from the bottom part, is going to be what? Is going to be tensile, while from the neutral axis to the top part is going to be what? Is going to be what? Compressive. All right, so take note of what we have here. So if we make our maximum stress the subject, we are going to have, sorry, love my work to be well arranged. So let's make it the subject here. So our M will be equals to our tensile here. So this is tensile. Our Y2 will be tensile. Multiply by what? Multiply by I. All right. So our Y that is tensile here will be equals to the value of our Y, the value of our Y bar, because our Y bar is the distance of the center of gravity from the bottom of from the bottom face to the what? To the neutral axis. And I just established the fact that if you look at our distribution diagram, from the bottom to the neutral axis is what? Is subjected to what? Tensile stress. So it shows that here we are going to have our M to be equals to, so it shows that our YT here will be equals to our Y bar. All right, so here we are going to have our stress here. Our tensile stress is given to us to be what? 20 multiplied by our I. Our I here is 9655 4667 point what? 0.21, then divided by what? Divided by our Y bar, which is 90.66. all right, so our maximum bending moment, if you press this in your calculator, you are going to have our value to be 21,300 389 point what? 0.85. So this is maximum bending moment. Our unit is going to be what? Newton mm. All right, so that is it. Now don't forget, the question says we should find the safe uniformly load which the beam can carry. So for us to do that now, we are going to recall that if we have a simple supported beam that carries a uniform distributed load, what is the formula for the maximum bending moment? So the maximum bending moment there will be equals to WL squared divided by what? Divided by 8. All right. So don't forget, we have gotten our maximum bending moment. This is our maximum bending moment here. It is 300 389.85, which is equals to W multiplied by length. The length is given to us to be 5, so it's going to be 5. Don't forget it's in meter, so 5 square divided by what? Divided by 8. So if we make W the subject here, W will be equals to 8 multiplied by what? 389.85 divided by divided by what? 25, but it is in meter, right? So we are going to multiply by 1000 in order to take it to what? Mm. So it's going to be divided by 25, which is in meter. Then if we multiply by 1000, we are taking it to what? Mm, because everything that we have here is in mm. So if you press it in your calculator, the value of W that they want you to find here is going to be what? It's going to be nothing but what? 6816 point what? 0.125. 125. So what will be the unit? The unit is going to be what? Newton per what? Per meter. So it's going to be Newton per meter. All right. So here is the first solution. All right. So the second thing they want us to calculate, let's say we should find the maximum compressive stress, right? So the maximum compressive stress. So we are still going to be using this formula for that. All right. But before we proceed, we cannot use the value of our tensile our yt for this calculation here. So we must find our y subscript c. So our y subscript c is the value of our y tensile, right? So which is going to be from the top part to what? To the neutral axis. All right. So we have gotten from the bottom part to the neutral axis, which is 90.66. So for us to get from the top part to the neutral axis is going to be the total distance that we have here, which is 200 plus 20 plus 40, which is 260. So it's going to be 260 minus 90.66. So 260 minus 19.66 is nothing but what? 169 point what? 0.34 mm. All right. So, but don't forget, they want us to find what? The maximum compressive stress. So it means that we are going to make this stress here the subject, and we'll put a C here. So we are going to say maximum compressive stress will be equals to m over I multiplied by y, but it's not going to be just y, now it's going to be y subscript what? C. So we are going to have this to be m multiplied by y subscript c divided by what? Divided by I. So if you substitute now, our m is going to be the same as what we have here, which is a 300 89.85. Then multiply by what? Our y subscript c, which is 169.34. Then divided by what? Our I. Our I is nothing but what? 96.4667 point what? 0.21. All right. So if you press that in your calculator, you are going to have your final answer for that. So our final answer for that is going to be 37.357. 37.357. So what will be our unit? Our unit is going to be what? Newton per what? Mm square. So this is going to be Newton per mm square. So this is the solution to the above question. I believe we understand this question correctly. I would have loved to draw the stress diagram, but you can watch our video on stress distribution. I have explained all of these concepts there if you want to see the stress diagram. Stress diagram is just something like this. It's just something like this. Just something like this. So here we have our tensile here, and then here we have our compressive. our compressive stress here. So this is how it is. So that is it. So you can watch our video on that. So thanks for watching. Please, if today is your first time of coming across our video, please don't forget to share this video with your friends who might be in need of this, and don't forget to give this video a thumbs up, and don't forget to subscribe and click on the notification bell, so whenever we upload a video like this, you'll be the first person to receive the notification. Thank you. Stay tuned for more interesting question and calculation on bending stresses in a beam on symmetrical section. Thanks.